Hello all, my name is Krish Naik and welcome to my YouTube channel. So guys, in this specific video, we are going to implement an amazing hybrid search RAG application. Initially, we will go ahead with the theoretical understanding about hybrid search, and then we will proceed with developing an amazing end-to-end project where we will be creating vector database even in cloud. We will be using vector database like Pinecone, and we'll be seeing that how we can implement an hybrid search on a specific vector database. So all these things will be covered in this particular video. So let's go ahead and enjoy this video. So before I proceed, guys, here is a quick announcement on this 3 amazing course that I have recently launched in Udemy, which is at a very affordable price. That is nothing but 399 rupees INR. You'll be able to find out the link in the description of this particular video. So here you have this complete generative AI course with Langchain and Hugging Face. Then you have this complete machine learning and NLP bootcamp, MLOps deployment. It has somewhere around 78 hours of content, which is quite amazing. And I'm also updating this content again and again as new things comes up. And there is also another course which is called as Building Gen AI App, 12 plus hands-on project with Gemini Pro. So you can go ahead and check it out, any of these courses, if you really want. It'll be available in the description of this particular video. Hello guys, so in this video we are going to discuss about something called as hybrid search. Okay, and this kind of search specifically we use in our RAG applications also, right? So till now, if you are following all the modules, the RAG that we have specifically created, let's say that if I have documents, let's say if this is my documents, then what we do is that we try to divide these documents into chunk of documents. Let's say this is D1, this is D2, this is D3. Like this, we usually divide into multiple chunk of documents, right? And this is DN. Now, after dividing all these documents into chunk of documents, then we specifically convert this into vectors, right? So here we are basically converting into embedding vectors. Then after we convert all this text to vectors, the next step is that we store all these vectors in some kind of vector database. Right. So let's say one of the vector databases that we have already seen, vector database. We also say it as something called as vector store DB. Right. Now, once this entire information is basically stored over here, right, it will be stored in the form of vectors, right? We will be having some kind of numbers over here itself, right? Now, when a user queries, whenever a user queries, right, over here, then what happens usually in this particular scenario, this particular query is also converted into vectors. And then a vector dense search or vector search is basically done. Vector search is basically done in this particular vector database. So once we have this particular vectors, we do a vector search from this particular vector database. And here, some of the algorithms like over here, one of the algorithm that may take place over here for basically to match the exact vector search, we can actually use cosine similarity, right? And based on this cosine similarity check, we will be able to get the response, right? And once we get this response, we can combine this with our prompt template plus LLM model. And finally, we can summarize any information as my final output, right? So in this scenario, you will be able to see that the kind of search that we are doing, right? The vector dense search. This search is basically called as semantic search. Semantic search. Semantic search basically means we are trying to find out the similar vectors from this particular vector database, and based on that, when that similarity search is done, we are able to get the response. And this kind of RAG, most of the RAG application uses this kind of search. And if I talk about vector databases like Fias, Chroma, right? They have this entire features like this, right? But I really want to talk about one more amazing search mechanism, which is called as hybrid search. Okay, so here I have this hybrid search. Now inside this hybrid search, here we are just not focusing on only vector dense search mechanism, right? Here we specifically combine multiple search techniques, right? And what kind of techniques we will specifically apply over here? We will be combining multiple search techniques. Now, specifically, if I really want to divide all this particular technique, one is the semantic search. The second one is something called as syntactic search. Okay. Now, I will talk more about it. What exactly are this kind of search basically? So one is semantic search, one is syntactic search. Semantic search specifically, we say it as a dense vector search. So here we are specifically trying to search elements that are similar, right? And obviously when we are using this dense vector search, we basically are checking out the similar kind of content, right? If I probably say with respect to syntactic search, right? Or I can also say this as exact search. I can also say this as keyword search, right? Keyword search. And if I also want to probably provide some more names like exact search and keyword search, and this usually happens with respect to a sparse, or I can also say this as sparse vector search. So here you could see in semantic search, I have a vector store, right, which has all the vectors embedded over here, right? So here all my text is basically converted into dense vectors, and this dense vector is basically stored in my vector store DB, right? In the case of syntactic search, you will be able to see that we will be having sparse metrics. So all this text will basically be converted into sparse metrics. Now, if you remember, or if you know, right, what is sparse metrics and how do we get a sparse metrics? If you know about these techniques like one hot encoding, bag of words, or TF-IDF, right? Whenever we try to use these techniques, we will be able to convert our text into sparse metrics. Now, when we say sparse metrics, that basically means there will be maximum numbers of zeros and ones, right? Wherever a specific word will be available in a sentence, that will be one and remaining all will be zeros, right? So this is basically called as a sparse metrics. And with the help of this sparse metrics, here we are just focusing on a specific keyword like this keyword, right? Whatever keyword we are actually trying to search. And this sparse metrics also has some very important properties, because from this we will be able to probably do the keyword search itself. And this is nothing but it can also be considered as an exact search. So in the case of hybrid search, it is just going to combine both this particular techniques, that is semantic search and syntactic search, or I can also say this as exact search or keyword search, right? It is just not going to be dependent on one of the search mechanism. And similarly, there are different kind of databases that are available. Just to show you as an example, like there's a database like Cassandra, right? We will be using a library called as Casio, right? And with the help of this Casio, you'll be able to see that we'll be able to access the Cassandra database. I will show this as we go ahead, okay? But right now, just try to understand over here what exactly hybrid search is doing, right? It is combining multiple search methodologies. And if I probably talk about in most of the e-commerce website and all, hybrid search is definitely implemented in the backend, okay? Now let's go ahead and see that how does an hybrid search work, okay? So here, we will go ahead and write how does hybrid search work. So let's say uh, in the case of hybrid search, what happens? Let's say if I have a specific documents. For all these documents, when we are storing this, uh, when we are storing this in our vector database, let's say this is my vector database, okay? And this vector database supports both, right? What does it basically supports? It supports vector search, dense vector search. Along with this, it also supports keyword search. It has both this particular property, right? Now, whenever I have this particular document inside this particular database or inside this particular vector store DB, these documents will also be converted into a sparse matrix, right? By using techniques like TF-IDF or bag of words. So this kind of embeddings, it will be converted and it will be stored inside this particular vector database. Along with that, for the same documents, we will also try to convert this into vectors, which will be my dense vectors. Dense vectors does not have maximum number of zeros or ones. Okay, that is the difference. And we will try to store this particular vectors inside this particular vector store DB. And again, here you can use different techniques. The techniques can be anything as you want, like we have seen, right? We have used different embedding techniques. We have used OpenAI embedding techniques. We have used Ollama embedding techniques, or if you want Hugging Face embedding techniques. So by all these embedding techniques, we can convert our text into dense vectors and we can store this in this particular vector database. Now, the idea is very simple. Since we are storing this in both this particular format, sparse matrix and dense vector matrix, whenever a user puts up any kind of queries, now with respect to this particular query, I will be able to retrieve two different kind of result. Okay. One result will be something related to my exact match or exact search or keyword search. And with respect to this keyword search, let's say whatever results I am getting, it will be my top K results, right? This will be based on this particular keyword search or exact search. So here, keyword search, I have written it downwards, right? So here you'll be able to see that whenever a user probably queries any information over here from this particular vector database, first of all, for the user query, again, their query will also be divided into two types. It will be converted into two types. One is the sparse vectors and the other one is something like dense vectors, right? So both these vectors, it will be converted. Then this based on the sparse vectors, here we are specifically going to get the keyword search and here we are going to get the results, right? Let's say the top K results I'll be getting over here. Based on this dense vectors, I'm actually going to do the vector search and again, I'll be getting another results over here, right? Let's say this is my result one, top K result one, and this is my top K result two. Okay. Now top K result one and top K result two are specifically there. This is basically done on the vector search, which is nothing but it is a semantic search. This is basically a semantic search, similar kind of elements. And this is nothing but this is a keyword search, right? Based on the sparse vectors that we have actually taken. Now in hybrid search, what we do is that we combine both of them based on weightage. Okay. And then we finally get the final response. Now the question rises, how we are going to probably combine this particular result one and result two to weightage based on this information that we have got. And finally, when we get the response, we can then further combine this with our LLM model and summarize this entire data. Okay. That is something separate. But still the question rises, how do we combine result one and result two and how based on weightage we take our final result, right? Final result. And that is what we will be seeing in our next video. The technique is very simple. The technique name is something called as reciprocal rank fusion in hybrid search. Okay, in hybrid search. So this technique we will be discussing in our next video, which will be the core behind this particular hybrid search. But the idea is very simple. In hybrid search, we take a combination of two different things. we try to do the search based on semantic synthetic, which will be the combination of dense vector search and exact search or keyword search. Okay, so both this particular technique we basically use. When I say top K result 1, top K result 2, that I may get 5 results, right? Based on the keyword search, I may get 5 results based on the vector search, something like that, right? So guys, now let's go ahead and proceed with the discussion with respect to reciprocal rank fusion and hybrid search. As I said, whenever we try to query or whenever user queries from this particular vector database, which supports both vector search and keyword search, which is a combination of semantic search and exact search. Over here, first of all, to get the keyword search, we have to convert this into sparse vectors, and this sparse vectors will be probably searching from this particular vector database, and we get top K results. Similarly, with the help of dense vectors, we also get a vector search, and here we are going to get a result 2, that is top K results. Okay. Now, combining both of them, we have to probably consider a response, right? How to probably get the final response, that is what I'm actually going to discuss now. Okay. So here, with the help of reciprocal rank fusion and hybrid search, we will be considering two important things. Okay. Let's say this is my vector database. Okay. And from this vector database, you know that whenever user queries, so based on this queries, let's say if this is my dense vectors, first we are going to do the vector search and we are going to get the top K results, right? So when I say top K results, let's say that this is my first document, right? And this can be my second document, right? And this can be my third document. Like this, I will be getting a lot of documents. Similarly, over here, based on my sparse matrix search, that is the keyword search, that is nothing but keyword search, I'm actually going to get my top K documents. So here also I will go ahead and draw this. So let's say here I'm going to get some other sentences. Okay. And the ordering will be different, right? So here, let's say this is the order that I've actually got. I got document 1, 2, 3, 4, 5. Let's say the 5 documents I've actually got. And here also we have got some other documents. So let's say some other documents, but here the numbering is different. Let's say the numbering is like 4, 3, 2, 5, 1. Okay. The numbering is different. This is my result 1 top K documents, and this is my result 2 top K documents. Okay. Now considering this, say here I've got in this ordering, that is 1, 2, 3, 4, 5 sentence, that is that I got in my top K like document 1, document 2, document 3, document 4, document 5. Similarly over here, document 4, document 3, document 2, document 5, document 1. This is the ranks that we have specifically got. Now how to calculate the final score, because here this is based on my semantic search, this is based on my keyword search. When I say semantic search, that is basically based on cosine similarity. Okay, so we are trying to find out the similar vectors and then we are trying to find out our final score. So in order to calculate the final score, the formula is very simple. Here we'll write summation of 1 divided by a constant plus the rank of documents. Okay, now this particular constant, that is C, it depends on various database. It depends on various databases. Okay, now with respect to various databases, this may range between 1 to 60. Okay, and this is a constant, guys. Okay, in various databases they'll set this value to 10, 20, in some of the databases I've seen the value to 60. Okay, so since this is a constant, we are just not going to focus much into this. Instead, I will just take up this formula now, summation of I is equal to 1 divided by rank of T. Okay, since this is a constant, for calculating in every the rank of every documents will probably give you the same answer with respect to that particular constant, like same impact it may be creating. Okay, now how do we compute the rank, right? So for this particular sentence, you'll be seeing 1 divided by rank of D. So if I go ahead and compute this, this is nothing but 1 by 1. Okay, This is nothing but 1 by 2 because this is rank 2, right? This is rank 3, so I'll get 1 by 3. It is nothing but 0.33. Then here I have 0.25, and this is my fifth document. Let's say the rank is 5. I'm actually going to get 0.2. Okay. Similarly, in this particular case, this is my document 4, right? And if I try to compute this particular rank, okay, it will be again 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5. So that basically means the document of D4 is basically getting a rank of 1 in this keyword search. Here D4 is basically getting 0.25. Okay. Now when we try to combine the final score, okay, this is important. See this. So if I finally go ahead and take up document 1, so if this is my document 1, and if I try to calculate the overall rank, then what we have to do? We have to do the summation. So let's see, document 1 is giving 1 over here and 1.5, 1 by 5. So I will just go ahead and write 1 plus 0.2. So this will be 1.2, right? Similarly, if I go ahead and calculate for document 2, right? So document 2 over here gives 0.5, right? So here I'm actually going to get 0.5 plus the document 2 over here is 1 by 3, that is nothing but 0.33, right? So here you can see I'm actually going to get 0.83. So this is my score that I'm actually going to get. And obviously this score is better than this score. So I will be getting the document 1 based on my 50% probability of 50% focus on keyword search, right? And 50% on semantic search, right? If you change the weightage, right? If you change the weightage, then you'll be able to see that some values may also change. Similarly, you have this document 3. And in the case of document 3, you'll be able to see that here I have 0.33. So let's calculate this 0.33 plus document 3 is nothing but 0.5. Again, here I'm going to get the same value, see 0.83. Now both these ranks are same, right? So if I want to retrieve the top K result, obviously this will be shown first. And then based on this too, right, where the focus is more, whether it is on keyword search or semantic search. Let's say if I say 70% focus is there on the keyword search, then over here you can see 0.5 value is higher than 0.3. So it is just going to give you the display the document 3 in the second rank, right? So this way the weightage can also be provided in keyword search and semantic search. Okay. And similarly, we go ahead and calculate each and every documents. So finally, you can see that here we can combine result 2 and result 1 top K elements, and then we can use this reciprocal rank fusion in hybrid search by assigning ranks, and we will be able to calculate a score, which will be finally given as a response. And here we can also assign weightage, and this can be combined with a prompt template, and we can summarize with our LLM model, right? So this gives an idea about the entire hybrid search, right? Now, in this section, in this next section, what we're going to do is that we're going to also see a practical example of how an hybrid search is basically done. But before that, if you know about one more search, right, that is based on graph knowledge search, okay, graph knowledge search. So in this graph knowledge search, I hope you may have heard about GraphDB. One of the most popular open source GraphDB is Neo4j. Okay. Now, if we are specifically using GraphDB to store the vectors, let's say if this is my database and this database is nothing but it is my GraphDB. In the case of GraphDB, I will be having like this nodes which will be connected with relationships, right? So this can be my node 1, this can be my node 2, and it will be connected with relationships. And we can, whenever a user tries to query, in this, there are 3 types of queries that happens. One is keyword search, which can also be called as semantic search. This can be also called as synthetic search, or it can be also called as exact search. Then along with this, it's also suppose semantic search, right? And finally, you'll be also able to see that it supports keyword search, semantic search. Along with this, one more search is there that is called as graph knowledge search. graph knowledge search. So it supports all these techniques, which is quite amazing. Just imagine hybrid search just supports this two type, but now with this help of graph knowledge search, we will still be able to create a very good efficient RAG application, right, with the help of GraphDB. And this we will be seeing about GraphDB in the upcoming videos, in the upcoming sections. But let's go ahead and see some practical example for hybrid search. Hello guys, so we are going to continue the discussion with respect to the hybrid search, and here now we are going to implement a complete amazing project with the help of hybrid search using Langchain. Now for this we will be using a vector database which is called as Pinecone. Now Pinecone vector database provides you this both, right? Like you will be able to do the keyword search, you will be able to do the semantic search. So let's go ahead and first of all we will set up our account, and then with the help of code we will try to write each and everything, and we'll try to probably go ahead and create our the vector database itself. So first of all, just go ahead and sign up over here. It is completely for free. First two to three instances you can create completely for free. So I have already signed up, so I will go ahead and log in. You have to just go to pinecone.io. Now once you go inside this, you will be able to see that I have already created one Pinecone hybrid search, right? And if you go inside this, there are some kind of data that is already available over here, right? But as usual, we will not probably work with this, but instead we'll go ahead and create our new index. Okay. But since I really want to do everything with the help of code, so we will try to create the instance even with the help of code. So first of all, that you actually require is your API key. Okay. So just click on API key. Just make sure that this will be the default API key that will be provided over here. And you can also rotate the key values. Like you can probably go ahead and change it if somebody probably sees it, right? So here I will copy this particular key value, and then I will start my coding over here, right? So here I will be creating my instance, everything as such. Okay. Now just quickly to go ahead with, I have some good requirement.txt here. You'll be able to see so many different libraries, but for Langchain, obviously you require a lot of libraries. But if I probably talk about with respect to Pinecone, I will be installing some of the libraries over here. So let me quickly go ahead and just paste it over here. So I'll be installing Pinecone client, Pinecone text, and Pinecone notebooks. Okay. So these are the initial libraries that we will be requiring. So I have already done the installation since I don't want to make my video very long. So here you'll be able to see a green tick, and already the entire the installation has basically happened. Then I will go ahead and write my API underscore key. This API underscore key will basically be replaced with the values over here, right? So I'm just going to create this particular variable. You can also create an environment variable if you want. Okay, perfect. Now, since we are using Langchain, so please make sure that we will go ahead and import this from Langchain underscore community dot retrievers. I'm going to import a library, which is nothing but Pinecone hybrid search retriever. Now this class is responsible in doing both the semantic search and syntactic search, right? So keyword search, like it has the combination of both the sparse matrix and dense vector search. And for that we have to create a retriever, and this is the class that we are going to use. So let's go ahead and execute this. And after executing this, the next thing will be that we need to make sure that we first of all create our index in our Pinecone, right? Without this, it will be of no use. So here, quickly what I will do, I will just go ahead and import OS. Since I have already imported Pinecone, so I will go ahead and write from Pinecone import Pinecone, serverless spec. Okay. And then I will just go ahead and create my index name. Now index name over here, I will say, hey, this will be my hybrid search example, and please make sure that you give all this in a smaller letter, otherwise you'll be getting an error. So I will say, hey, hybrid search Langchain Pinecone. Okay, so this will basically be my index name. Okay, once I probably create the index name, we have to initialize the Pinecone client. Okay, then for initializing the Pinecone client, I'll write PC is equal to Pinecone, and we will initialize with this API key that I have actually created, right? So over here is my API key. You can create your own API keys, no need to use mine, okay? Because as soon as I upload this video, this will get deleted, okay? Or I'll rotate the key. Then we will go ahead and create the index, and here I'm going to basically write if index underscore name is not in pc dot list indexes, right? We are listing all the indexes. If this particular name is not there, then only we should probably go ahead and create this. So I will write pc dot create index, create underscore index, and here I'm going to give my name is equal to index underscore name, whatever index underscore name we have specifically taken. Whenever we try to create an index, we also have to give our dimension. Okay, so here like what will be the vector dimension? So here I'm going to use the vector dimension is equal to 384. The reason is very simple. The reason why I'm using, and this is nothing but this is my dimension of dense model, okay, dense vector. The reason is very simple why I'm using 384, because the embedding technique that I'm actually going to use is a Hugging Face embedding technique, which is nothing but sentence transformer that by default converts any text into 384 dimension. So that is the reason why I'm creating this particular index with this dimension, okay. Along with this, the next thing that I'm going to use is metric. So for my metric here, I will be using a dot product. So this is all information you specifically get when you are creating an index. Let's say if I go to over here and create my index, so it's ask you for the dimension, right? Over here by default you can see metrics also, it asks you whether you want to go with dot product, cosine and all, right? You can select any of this particular metric. So that is the reason why I am giving a metric over here, right? So I'm saying, hey, just go ahead and do it, the dot product, okay? And this dot product specifically I am going to do it for sparse values, right? Sparse value supported only for dot product, because we are creating this hybrid search for both of them, right? And then finally you have the spec is equal to for this particular spec I will be using serverless spec, and I have to probably give my cloud information like AWS it is and which region. This also you'll be able to get inside that particular so I will just go ahead and write US East 1, okay. So if you remember, just now we saw this particular index also. So if I go ahead and see this, here you have the serverless, okay. All the information is over here, let's say. And here you can select this US East 1 and all. This is locked. So that is the reason I've written this. I've selected AWS. If you go ahead with Google, you have to go ahead and write this, right? So this is just a starter plan to go ahead with. So I'm going to use this free one, okay. Perfect. So let's see whether this gets executed. So here I think everything looks good enough. I have my index name, pc.create, and here I will just write comma, okay. Okay, just a second. I will just update this entire thing. Okay, perfect. Now this looks good, exactly, right? I have all the details. Now let's go ahead and create this index. So here you will be able to see it will take some amount of time to create this index, but this is going to get created directly inside our vector database. So now if I go ahead and click on index, if I reload this, I think it should get created. Okay, so here is my hybrid search Langchain Pinecone, and right now the dimension is 384. I don't have anything. The metric is dot product. The reason of using metric is that I really want to support both. That is for my sparse metrics and my vector index, right? So here I have my all details. Now let's go ahead and further do the more coding over here. I have already created my API. Now let's click on my index and I will say, hey, pc.index. Okay, pc.index. And here I'm just going to give my index underscore name. So let's go ahead and see this index over here. So this is my Pinecone index at this particular memory location, and obviously my index name that you'll be able to see over here, that index name, based on this index name, I'm trying to take out that details. Okay. Now, first thing first, you know that, right? Our entire project is a combination of two different. One, I'll try to create a vector embedding, and the other one, I will try to create a sparse matrix. Okay. And that is what hybrid search basically tells you to do it, right? So first of all, what I will do, I will go ahead and import OS, and here I will write from .env import load underscore .env. Okay. and we will be loading all our environment variables, right? Now, just to give you an idea about the environment variables, since I'm going to use an open source embedding technique from Langchain, from Hugging Face itself, so I will go ahead and import from Langchain underscore Hugging Face. Okay, I'm going to import my Hugging Face embeddings. Okay, and here one of the embedding technique that we regularly use, and with respect to the same dimensions, I'll be using this Hugging Face embeddings, and here I'm going to use my model underscore name is equal to all dash mini. This is a sentence transformer LM L6 and version v2. Okay, so this will specifically be my embeddings. So here let's go ahead and see the embeddings over here quickly. Yeah, so my embedding is getting downloaded, and this will probably take some amount of time, and here you can see the word embedding is nothing but 384. Please note, before doing this, if you directly execute it, it will not work, because the reason it is working, because I have already imported os.environ. You have to create this Hugging Face token, right? hf underscore token, and this is already present in my environment variable. So I will go ahead and write os.getEnv is nothing but hf underscore token. You have to execute along with this. If you do not have the hf underscore token, this will not get loaded. Okay, so please make sure that you have this particular code. Perfect. So this was it. Now let's go ahead and execute it once again, and now I will be having my entire Hugging Face embedding. Now this embedding technique is used to create your dense vectors. If I go ahead and proceed further, for my sparse metrics, I'm going to use one more, that is Pinecone Pinecone underscore text. For my sparse, there is an encoder which is called as BM25 encoder. Now this particular encoder uses TF-IDF by default. Okay, TF-IDF techniques. So here I'm going to write PF25 underscore encoder. Okay, is equal to nothing but I will just go ahead and initialize this encoder, and I will say, hey, use the default one, which is nothing but TF-IDF. Okay, and this basically becomes my BF25 encoder. Okay, and this is responsible in doing the sparse metrics conversion for any queries or for any text. Okay, now I hope you are very much clear with all these things now, and you are able to probably do all these amazing stuffs and all, right? Now I will try to create some sentences. Let's go ahead and create some sentences, and this sentences will be a list. Okay, and just to show you one example, I will just be creating some sentences over here with respect to this particular list. I will have this 3 sentences. Let's say in 2023 I visited Paris, in 2022 I visited New York, and in 2021 I visited Orleans. Okay, now I will take all this information and quickly I will go ahead and write BM25 underscore encoder dot, we are just going to fit on these entire sentences. Okay, so once we do this, in short, we are just applying TF-IDF values on this sentences. Okay, perfect. So once I do this fit, along with this, what I will do, I will store the values to a JSON file. Okay, so here I will just go ahead and write PF BM25 encoder dot dump. Okay, now I'm going to basically dump my BM25 underscore values in the form of .json. Okay, and here you will be able to see that I'm actually dumping this entire information. You can also go ahead and load this just to make sure that you have that entire dump. Okay, and you can also load it. So has no attribute dumpy. Okay, it was dump, no worries. Okay, so now here you can see that I have my encoder, and this is specifically for sparse metrics. Okay, now one more thing that you will be able to see over here is that once I do this particular sparse metrics dump, so I've actually created the sparse metrics for this, right? Now let's go ahead and create my retriever, and this retriever will be important because with the help of this specific retriever only, I will have the combination of both the embedding techniques and obviously the sparse embedding techniques, right? So for that, I will go ahead and create this Pinecone hybrid search retriever, and here I'm going to use my embeddings is equal to whatever embedding technique I have used, that is nothing but Hugging Face embeddings, and then my sparse encoder, which will be assigned to my BM25 encoder, and I have to also specify my index, right? So this will basically be my index. Now once I execute this, this is my retriever. Now with the help of this particular retriever, it supports both embedding, the vector dense embedding technique, and along with that the sparse metrics. Okay, so this is my retriever. So I'll just go ahead and display my retriever. Okay, so this is my retriever, and this is the entire information that you'll be able to see, right? So finally, let's do one thing. Let's quickly go ahead and add all the text that I want, right? So I will say, hey, we will go ahead and add the text, and the text that we are going to add is all my sentences inside my index, right? So what are my sentences? Here you go. I will copy this and I will paste it over here. Okay. So let's go ahead and execute this. Now here you'll be able to see that it will get inserted inside that particular index, right? The index, the Pinecone index that we have created. Now it's time we can probably retrieve any results. First of all, let's see whether it has got inserted or not. So if I go over here, you can see it's loading, and all these 3 sentences are now available, and this is all 384 dimensions, right? So this one in 2021, I visited Context, Orleans. In 2023, I visited New York, Paris, and all, right? Now let's go ahead and ask some questions, and this time it is going to use the combination of both, right? Your vector dense search and the other search. So here I'll say, with what city did I visit last? Okay. So here you'll be able to see visit last. So here you can see in 2021, I visited New Orleans, then New York, then visited Paris. All this page content is basically able to come over here. It is used both because this entire hybrid search retriever is using both embeddings and the sparse metrics. Okay. If I say recent, so in 2021, all this information is basically coming up. Okay. Which city did I visit first? Okay. So here you can see in 2021, I visited New York. So all the information are basically, you're able to see it over here. But internally, it is taking a combination of both hybrid search, and this is what is an amazing example, which you can also go ahead and do it. Okay. So I hope you like this particular video. I will see you all in the next video. Thank you. Take care. Bye-bye.